In this talk, we'll discuss VisSnippets, a web-based system for impromptu collaborative data exploration on large displays. Science is widely and rapidly moving to a new paradigm called data-intensive scientific discovery. This new paradigm is changing the way that science is conducted, and to support this transition we need first a foundation on which scientists and analysts can work with their complex, heterogeneous, multidimensional, domain-specific data in order to help identify and understand their problems. Additionally, we need a shared context in which mixed expertise groups of users, including scientists and analysts, can collaborate effectively in order to answer their questions. To this end, we have created VisSnippets. The VisSnippet system is a collaborative, exploratory programming environment in which these groups of users can collaborate and work with their data. The VisSnippet system is built on Sage 2, utilizing the windowing and content management capabilities of its shared collaborative workspace. VisSnippets adds to this workspace an environment for visual data exploration. While working with VisSnippets, users write snippets of code in parallel for operations such as retrieving data from a remote API, cleaning and transforming data, or to visualize the data using their favorite charting library. These snippets serve as building blocks of analysis. Once created, snippets are added to the group's collective pool of analysis blocks. The web interface on a user's personal device provides a snippet editor which allows users to create, manage, edit, and debug snippets and their execution. Additionally, a dataflow meta-visualization shows a user the current analysis structure. Any snippets from the group's collective pool of work can be composed with one another, and new snippets can be attached to any stage of the current analysis. Each time a snippet is composed onto the data pipeline, new reactive data flow is created. Whenever a snippet is edited or new data is available, the updated output will automatically propagate downstream to any subsequent data flows. From the VisSnippets editor, users can select a snippet which they would like to add to the pipeline. Next, the user chooses the target which they would like to use as the input of the snippet. Once created, each data artifact or visualization can be rearranged or resized within the workspace. Next, we will take a deeper look at the design of VisSnippets and its motivation. The design of VisSnippets is motivated by two primary aspects. First, VisSnippets must support expressive analysis. Second, it must do so during mixed-focus collaboration. When we talk about expressive analysis, we refer to the flexibility that a system offers to adapt to different types of data from multiple domains. Supporting expressive analysis will make a system more broadly useful to multiple user groups. Within the realm of visualization toolkits, there exists a similar idea of expressiveness. You can plot visualization toolkits on a continuum between the most accessible to the most expressive. Tools like Excel or Tableau are more accessible and have a lower barrier to entry, but afford less flexibility to users in the types of visualizations which can be created. The most expressive tools like WebGL or D3 require programming, but the low-level control provided allows them to be useful for nearly all types of analysis. The growing popularity of computational notebooks such as JupyterLab or Observable show that users across scientific domains value the model of exploratory programming for data analysis. The foundation of exploratory programming also provides users with the flexibility to use nearly any visualization toolkit or data analysis library that they desire. Within exploratory programming, prior research has shown that analysts prefer to work with small scripts for incremental analysis and live or reactive programming environments. Exploratory programming as the foundation of VisSnippets provides users with control over how they interact with each data point in their analysis. Choosing JavaScript allows for the integration of most common web-based visualization libraries like D3. The large display implementation of VisSnippets also provides users with space to think. Space to think refers to the ability for users to outsource memory to the display, reorganizing or grouping content as a method of applying a semantic layer to the information. Large displays also provide space to perform subjunctive analysis, simultaneously exploring and comparing alternate scenarios in parallel. Towards the concept of expressive analysis, the flexibility in spatial and collaborative organization, in addition to the freedom during implementation, allows users to integrate their data and domain-specific semantic understanding into their analysis. While flexibility in analysis is important, it is also critical that users be able to work together to solve their problems. During collaborative analysis, mixed-focus collaboration describes transient states of individual and shared group activity. As an example, when users are disjoint, they may be working entirely independently on different problems. During loosely coupled work, users may quietly and independently work on different sections of the same problem. During closely coupled work, users might discuss results they found independently, but collaboratively synthesize new information. Closely coupled collaboration has been found to be effective for completing analytical tasks, but loose coupling can also be effective if there's a low cost to integrate parallel work and common ground between collaborators is maintained. In addition to the space to think provided by large displays, these large collaborative workspaces are also effective in allowing for individual content ownership and workspace partitioning during parallel work. The design of VisSnippets encourages parallel exploration by allowing each participant to choose their analysis methods and claim a section of the shared workspace. Within this shared workspace, the transparent data flow architecture elucidates the collaborative analysis and provides data provenance, acting as a form of common ground between users. Our open source utility to summarize data artifacts, seen in action on the right, distills their structure and data types to aid in establishing a common interface between snippets written by separate users. The branching data pipeline structure and data summarization utility are each designed to reduce the cost to integrate parallel work. Next, we will take a look at two example applications built using VisSnippets. For each application, we will walk through the analysis implemented and discuss the efficiency in creating these linked visualization applications in terms of the total source lines of code required from users. The first application looks at power consumption data from the City of Chicago data portal. This is open data containing energy usage information for less than 1% of buildings in the city, which account for an aggregate 20% of energy used citywide. This is an exploratory analysis of data, where the goal is to identify trends or outliers in the data to guide analysis to identify contributing factors to energy usage. The first step of the analysis is to retrieve the data for these buildings using the Chicago Data Portal's REST API endpoint. Next, as a basic overview of the data, this snippet computes a few pieces of information to summarize the data set, including the list of community areas, the number of property types, and the minimum and maximum value for gas and electricity usage out of this list of buildings. Using the initial data retrieved, this snippet uses the D3 library to create an interactive bubble chart plotting electricity usage on the x-axis and gas usage on the y-axis. Additionally, the color of the bubble represents the number of buildings in the community area, and the size indicates the average square footage. Clicking on a bubble will select that set of buildings in that community area for use in subsequent analysis. Here, a snippet is written using the Vega Lite charting library to plot buildings based on energy usage versus year built. This snippet is applied twice in the analysis. First, the snippet is composed onto our initial data set to visualize this information for all buildings. Next, it is composed onto the interactive bubble chart, plotting only the filtered subset of buildings. The snippet was applied identically using two different data sets, showcasing that snippets can be reused at multiple stages of the analysis. In this case, it is being used twice in order to perform a part-to-whole comparison within the data. Lastly, another bubble chart is used to plot the property type versus year built for all buildings in the city to provide an overview of the data set. This interactive analysis was created using only 170 lines of code written by users, including comments and whitespace, around 100 of which was used to create the custom interactive bubble chart. The second example application is an interactive transportation dashboard. This application uses real-time bus data from the San Francisco Next Bus Data API. The goal of this application is to provide a real-time dashboard which will allow a user to monitor a fleet of buses and to identify and address potential issues that arise. The starting point of this analysis is a snippet which retrieves the name and tag of all bus routes from the Data API. Using the set of routes, the next snippet retrieves and summarizes each route based on the number of buses and their average speed. The route summary is then visualized using two Vega Lite bar charts to plot the bus count and average bus speed for each route. The same snippet to create the bar chart was used twice in this scenario, utilizing a built-in declarative API provided by VisSnippets to add a text parameter to the snippet. The text parameter in this case selects the attribute to be plotted on the y-axis of the chart and can be entered and updated for each instance of the chart without editing the code directly. Branching separately from the initial list of routes, this next snippet creates a list of all route tags, which acts as an interactive route selector. Based on the user-selected route, this next step retrieves the set of all buses for that route from another endpoint on the next bus API. This snippet uses another declarative API provided by VisSnippets to rerun the code periodically every 5 seconds. Using the set of all vehicles for the selected route, this last snippet plots all the buses on a map using the leaflet mapping library. This interactive dashboard was created using only 145 lines of code written by users. The result is a linked application which interacts with a live external data source at multiple locations within the analysis. To create this application, a user familiar with the data API may set up the communication with the API and create the route selector. A second user who is experienced using Vegalite can create the bar charts, and a third user experienced in geospatial visualization can create the map of bus locations using Leaflet. These two example applications showcase the diversity of analysis supported by VisSnippets. The type of data, task, and visualization methods used are all different between the two applications, but each analysis was supported with very few lines of code. VisSnippets has some shortcomings which we would like to address in our future research. First, the expressive foundation of VisSnippets is important, but it could benefit from more built-in snippets or snippet templates to reduce the barrier to entry of the system. Second, the branching model is powerful for exploratory or subjunctive parallel analyses. However, VisSnippets could benefit from a way to join results together in the later phases of analysis when synthesizing information after the exploration phase. Lastly, VisSnippets is designed to support mixed-focus collaboration with low-cost integration of parallel work, and this design is grounded in background research in the field. However, this has not yet been evaluated with a formal study. This system would benefit from a summative evaluation examining its efficacy in order to support the design instantiation as well as inform future work. In this talk, we discussed VisSnippets. The VisSnippet system is designed to support collaborative data exploration by leveraging the model of exploratory programming. It does so in a shared workspace created using large displays. This research contributes to the design and implementation of VisSnippets grounded in prior research in collaborative visual analytics, large high-resolution displays, and visualization authoring. We present two example applications, an exploratory analysis and an operational dashboard, to demonstrate the flexibility of the VisSnippet system. Lastly, we discuss limitations of VisSnippets and potential directions for future work. Thank you for taking the time to learn about VisSnippets. For more information, or if you have questions or comments, please connect with us on Twitter or visit our website. Thank you.